Welcome. I am Zora Dawoodi at the University of Maryland, and this is part of lattice gauge theory for high energy physics traineeship course, and the topic is on effective field theories of hadronic and nuclear physics. So let's first understand what the big questions are in hadronic and nuclear physics today, so that we need to develop and apply effective field theories to apply to this. Let's go back to more than a century ago, to the discovery of nucleus by Geiger, Marsden, and Rutherford, which really marks the start of nuclear physics. It turned out that still today, there are major questions in nuclear physics that remain unanswered. Let me mention a few. We still don't know exactly what the nature of dense matter in the universe is and what constitutes, for example, the interior of a neutron star. What are the phases of a strongly interacting matter? By that, I mean matter that is governed primarily by the strong force in nature, quantum chromodynamics. In particular, we don't know as a function of density and temperature what phases and phase transitions and possibly critical points might exist in this phase diagram. We are hoping to explore the phase diagram experimentally using a number of experiments around the globe. And one of the ways that we would do that is to create rare exotic isotopes. And we think that they may give some clues. But in the end of the day, it would be really nice to know theoretically what the predictions are for these phases of matter. Still related to that question, we would like to know what processes occurred. For example, in core collapse supernovae and neutron star mergers, we need to know the state and phases of these matter, particularly in these violent conditions. We would like to know where the heavy elements on Earth come from. And again, we could try to explore these questions by making neutron-rich isotopes on Earth and understand their properties. One of the facilities in the US and funded by the Department of Energy and Michigan State University is EFREC, who is set to actually do this. So again, it would be nice to be able to provide theory input to an experimental program like so. Let's not go too far. Let's just think about not a collection of atomic nuclei or neutrons and protons in the universe, just a single one of them. Consider a proton or a neutron. We would like to understand the complex structure of these objects, what role the partonic degrees of freedom, including quarks and gluons, play in the structure of these objects. We would like to know whether the nature of a nucleon change when they are bound in a heavy nucleus. And again, importantly, we would like to know how important gluons are in the properties of the nucleon and nuclei. Obviously, this is a very complicated quantum many-body system, strongly interacting, and therefore exploring questions like this requires very precise theory as well as experimental tools. There's a big questions planned in electron-ion collider. The Brookhaven National Laboratory is going to answer some of these questions, and as theorists, again, we are striving to be able to provide theoretical input to this experiment. What other questions in nuclear physics are important today? Well, we would like to know whether fundamental symmetries of the standard model are violated. And that may mean that new interactions are in play in nature. It turned out that we use nuclei as a laboratory to make discovery in this area. And it is important to know how well these nuclei then interact with external probes. Let me give you examples of this. One is electric dipole moments of nucleon, nucleus, and atoms. If it's discovered to be non-vanishing, it's a sign of time reversal invariance violation in nature and could point to new physics beyond the standard model. And there are plenty of experiments out there that are setting limits on the electric dipole moments of various objects. Another example is what's called neutrinoless double beta decay, a process that, if discovered, would tell us the lepton number is violated, or the conservation of lepton number is violated in nature. The way we're trying to probe this process is by putting together a large mass of atomic isotopes, usually heavy isotopes like germanium. And we're looking for not the single beta decay, but double beta decay, but not the regular double beta decay, rather a double beta decay that does not give you any neutrinos in the final stage, rather just electrons. So if discovered, this would be important for our understanding of neutrinos. This would tell us that neutrinos are their own antiparticles. In other words, they are Majorana fermions. And at the same time, it would tell us that a standard model is insufficient in its current form to describe a process like this. Another example, again, in the realm of neutrino experiments, is neutrino oscillations experiments, which are searching for the violation of charge conjugation and parity, CP, in the universe. So again, an important example is the DUNE, or Deep Underground Neutrino Experiment in Fermilab, that is trying to search for these kind of oscillations in a long baseline kind of experiment. And it would be important to be able to constrain the parameters of CP violations in a standard model and hope to discover something beyond. Okay, so all of these experiments involve understanding the interactions of hadrons and atomic nuclei with either a standard model or beyond the standard model probes. And we would like to be able to understand and isolate theoretically the standard model contributions to these processes well, such that we can then identify what is left over, which would be new physics. Similar examples are in the realm of dark matter searches. Okay, again, in direct dark matter detection experiments, we are using a ton of atomic nuclei, again, things like germanium, on the ground to be able to search for candidates of dark matter particle, any signal that comes out of a recoil of a nucleus with something unknown that we cannot identify with the background might tell us something about a dark matter particle that hit that nucleus. So this would be exciting, and we are vigorously searching for this in the community. But at the moment, we only have set bounds and have not found signatures. So again, it is very important that we would be able to set these theoretical bounds in combination with experimental measurements precisely. In order to do that, we need to know how an atomic nucleus would interact with these external probes. There are other interesting questions which are more interesting from an intellectual perspective. For example, we can ask ourselves, have we existed if the input parameters of the standard model had been set differently in nature? What are some of these input parameters? Well, the masses of the quarks, the strength of the couplings in strong force, in the weak force, and so on. Would the nuclear physics as we know today exist if the quarks were lighter or heavier, for example, right? You can ask how the reaction rate of the chain of reactions that would eventually lead to carbon and oxygen on Earth would change as a function of these parameters, such that maybe there will not be enough carbon and oxygen produced for life to exist, okay? These kind of questions we can't really explore experimentally because these input parameters are set in nature. However, as theorists, if we have enough theoretical and computational power, we will be able to actually change these input parameters and seek the answer to these kind of interesting fine-tuning questions in nature. So there would be several exercises associated with this lecture, and I go through them one by one, and hopefully there would be time during the class presentation such that we can explore these exercises and try to address them together, okay? Let me just read exercise number 1. This is about some of these experiments that might exist in your region. It would be good to try to research and see what experiments are there near in your region, and what kind of questions among the questions that I just posed these experiments are set to answer. Okay, so these are all exciting questions. They're important for our understanding of nature, and they're important for understanding our role in nature from the sort of intellectual perspective. Why nuclear physics? Why do we exist in the form that we exist today, right? It would have been great if we can answer these questions from a fundamental level, okay? But how do we actually approach these problems? So let me give you sort of a historical view of how things developed in this field. Traditionally, everything was based on experimental data, which is great. You first try to measure a few, for example, cross-sections, reaction rates, and so on and so forth. And based on that, you will build what is called nuclear potentials in the few nucleon system, okay? Let me give you examples. For example, there are plenty of very accurate experimental data on nucleon-nucleon scattering. By nucleon, I mean protons and neutrons. And you can, for example, measure their scattering phase shift as a function of energy. And these are several plots that I've shown for various different phase shift associated with those experiments, okay? So then what do we do with this experimental data? We need a model to be able to fit to this experimental data. So we take two nucleons and we ask, how can these nucleons interact with each other at short distance, at intermediate distance, at long distance, okay? So there have been plenty of these potentials developed over the years and being matured. One of the examples that is very popular among these phenomenological potentials is the one that I mentioned here, AV18. It has 3 pieces. One piece is associated with the existence of pions in nuclear physics. Pions are important, and they turn out to exchange the nuclear force between the nucleons. There's a short distance piece, and there's another piece associated with the fact there could be electromagnetic interactions, in particular, if you have 2 protons that are interacting with each other. So then let me give you an example of one of these objects, the pion exchange potential V sub pi that I have here as a function of distance between the nucleons. It has this pretty complicated form. Something to remember is that this force is a Yukawa force. It is being mediated by a pion that has a mass m pi, and it sets, therefore, the range of these interactions. And then other than that, it goes then like 1 over r, okay? And there are a few other pieces over here. One is this complicated piece, which is called the tensor piece, which has also some sort of 1 over r polynomial dependence, and a complicated function of the spin as well as the isospin components of the nucleons, okay? This is just one of those potentials. Of course, there are many more. In particular, you can think about 14 operator substructures that would come out of just multiplying out the spin, isospin, and angular momentum functions of these nucleons with basically an isospin function. I'll talk about isospin in a moment. And there are 4 more, and that's why there are essentially 18 unknown coefficients associated with this phenomenological potential that need to be fit to experimental data, such that then you have a potential that you can make predictions with for other observables, other experiments, okay? So this is just one example. This is sort of a picture of what a potential like this could look like. AV18 is plotted in red, but there are other phenomenological potentials that have a slightly different shapes as well. And this is for nucleon-nucleon potential in what is called 1s0 channel. This is associated with two neutron channels, okay? And I talk about these isospin channels in a moment in an exercise. But one thing to note about this potential is that there is a long distance piece, that Yukawa piece that we just talked about. There is an intermediate range piece where this potential in this region is associated with the exchange of not only just a single pion, but multiple pions, but in principle also other heavier mesons in nature, okay? And then there's also a short distance piece called repulsive core. Of course, as you bring these nucleons together, there is a limit on how much you can do that. And we lose control because at some small distances, nucleons are not really the degrees of freedom of the strong force anymore. And we have to worry about the quark and gluon degrees of freedom. But it turned out that there is sort of this short distance piece that we can parameterize with a set of contact interactions of various form, okay? So pictorially, this is how these phenomenological potentials could look like. But potential is not a physical observable. It's kind of a scheme dependent. It would be nice to be able to calculate something that is physical and meaningful using these potentials. So then we have to take the potential and we have to solve the many-body Schrodinger equation, for example, in larger systems, where if we are interested in properties of an atomic nucleus, then we take our potential and then we assume that this potential describes this atomic nucleus properly, and then we solve the many-body equation, okay? So this is a result of what you can get out of the potential that I showed you, AV18, for the spectrum of various light nuclei up to carbon-12. And it is hard to see from the slide, but you should notice that AV18 almost gets these energy levels right, but not quite. And the reason being that it's actually missing on an important contribution, 3 nucleon forces. It is not just the potential between 2 nucleons that should be accounted for, but 3 nucleons can also interact, and 4 nucleons can interact in a way that is not described only by 2 nucleon forces, but rather these higher order forces. If you account just for the 3-body force, which is this AV18 plus Illinois 7 interactions, you actually get pretty close to experiment, which is remarkable, okay? So these phenomenological studies have been quite successful in a range of problems in nuclear physics. But we'll get to what the limitations of these models are in a moment. Exercise number 2 is to make sure that everyone is on board with the notion of nucleons, isospin, nucleon channels, and so on, okay? So in this exercise, we consider isospin symmetry, which turned out to be an SU2 symmetry in the space of up and down quark flavors. And it is a good approximate symmetry of strong interactions, okay? So now we want to consider 2 nucleon systems in nature under this symmetry. So again, up and down quarks have pretty similar masses. If we ignore their different electric charge, because we're not dealing with electromagnetism here, we're just dealing with the strong interactions. Under strong interactions, it turned out that they have similar interactions with other objects in the standard model, so they can actually put into an SU2 doublet. In the same way, each of these nucleons, the protons and neutrons, they can also form a doublet. Why? Because neutrons and protons are just different because of their different U and D content. They have different electric charges, but as far as strong interactions go, they are similar. They interact in a similar way with other objects in hadronic physics. So again, we can put them into a doublet, a SU2 doublet. So in this exercise, we're going to consider 2 of these nucleons, whether 2 protons, 2 neutrons, or a proton and neutron, and try to classify positive parity two nucleon systems according to their spin, isospin, and angular momentum. Something that you need to recall is that fermionic wave function must be totally antisymmetric under the exchange of the fermions. Okay. And each nucleon has a spin half. It has isospin half. In particular, protons are associated with the upper components of the isospin, and neutrons are associated with the lower component. And then I3 is the third component of isospin in this notation. So then we're going to write down these states explicitly according to their spin and flavor content. We want to see how many of those exist given this constraint of positive parity, totally antisymmetric fermionic wave function. And eventually you should ask yourself which one of these channels that you wrote down would exhibit a bounded state in nature. Okay, so again, we're going to go through this exercise hopefully throughout the class. Okay, so we talked about phenomenological models so far, not effective field theories yet, which is the topic of this course. So I have to then tell you why we are not convinced with these phenomenological models, and we want to do something more. So what is missing from these models? Well, first of all, we cannot really assign any uncertainty, any quantifiable uncertainty to the predictions of these models. It is not clear that the model fits, and we cannot improve them in a systematic manner. The reason being that you just give me a set of experimental data, I fit it with some model, well-justified model in principle, with certain parameters, and it can fit those experimental data pretty well with high chi-squared, but there is no guarantee that if you change the energy, the densities, and so on, you will still be able to describe data because the model that you have created is only a finite range of applicability to just the set of data that is being fed to. And in particular, it's very hard to know how far away from the model predictions you are, right? Once you give, you try to predict another phenomenon. Another problem is that there's no connection to the underlying theory of strong interactions, quantum chromodynamics. We know the theory of quarks and gluons and how they interact. On the other hand, we write in nucleon potential that doesn't seem to connect in a direct way to the interactions of the standard model. For example, something that we will talk about is chiral symmetry. We would like to write something that is respecting the chiral symmetry of and the chiral symmetry pattern, breaking pattern of the standard model, and these phenomenological models don't do that necessarily. Okay. Another important matter which is related to this second bullet point is the fact that these models are essentially unrelated to other strong interaction channels. So if you make predictions for certain scattering channels, how can you actually know whether those predictions could be useful for other strong interaction channels? If they were connected to the underlying interactions and their symmetry and symmetry patterns, in principle, we had a way to be able to make predictions for other observables that are related by symmetry considerations to other channels. Okay. And the last bullet point is really the fact that these phenomenological potentials, by their nature, are unable to answer several questions, such as phases of dense matter. Why? Because, well, they are not fit to data arising from experiments in dense systems. They're usually fit to dilute systems at low energies. So we don't really know whether we can push it and be able to make predictions for denser environments. They cannot answer questions about fine tunings in nuclear physics because they are not related to the underlying theory, and we don't know how parameters like the masses of quarks and so on would then appear in these phenomenological potentials, and therefore there's no way to be able to really tune them and see what we get. Okay, so these are some of the limitations of these phenomenological models that would motivate to think a bit more fundamentally about the problems in nuclear and hadronic physics. Well, how fundamental? Then obviously QCD, quantum chromodynamics, the theory of a strong force in the standard model, is describing all these phenomena. So ideally, we should start from QCD, right? So let me remind everybody what quantum chromodynamic theory is, and that means I'm going to show you the Lagrangian of quantum thermodynamics, okay? So QCD is an SU3 Yang-Mills theory that is augmented with several flavors of massive quarks. There are three types of terms in the QCD Lagrangian. The first term that I'm going to call the quark kinetic term and the mass term is essentially a bunch of fermions, Dirac fermions, with different flavors, up, down, strange, and in principle, 6 of those in the standard model, although the other 3 are pretty heavy compared to the light quarks. And then there are certain masses of these flavors of quarks that are appearing in this mass term in the QCD Lagrangian, okay? What about interactions? Well, quarks interact with gluons. This is an SU3 theory, and there are 8 flavors or 8 types of gluons associated with the QCD theory, and all of these 8 gluons would then interact with these quarks flavors, and these quark flavors also come in 3 types of colors, okay? So we have this term, which is just gauge invariant interactions between these gauge bosons of QCD, the gluons, and various flavors of the quarks. Importantly, in QCD, the gluons themselves interact. Not only you have the usual kinetic operator for the gluons, the F mu nu, F mu nu, associated with each of those colors of your gluons, you also have interactions between 3 and 4 of these gluons in a rather complicated manner that is well known and is gauge invariant. Importantly, the coupling constant associated with these interactions is rather set by the coupling constant between the quarks and gluons themselves. So there's only one coupling constant, which is a consequence of gauge invariance in this theory, okay? So we have these interactions for all purposes. We're not going to do anything with this Lagrangian for the rest of this course or this particular topic. All we have to remember in the end of the day are what kind of symmetries are relevant to this QCD Lagrangian. And we'll come back to this in a moment. Okay, so let's think about what features the QCD theory would present us. Okay, the first thing to observe about the QCD Lagrangian is the fact that there are really only 1 plus NF input parameters, the masses of the quarks, there are F flavors of them, and then there is one coupling constant. So if you then consider also the quantum electrodynamics coupling, that's another input parameter. And then once you fix these few input parameters using experimental data, then you can predict all aspects of nuclear physics, which is remarkable, right? So you start from a pretty complicated looking Lagrangian, but in the end of the day, there are only a few terms, and there are only a few input parameters. If you give me a few experimental data points, so I can fix those input parameters, in principle, I should be able to then predict everything else, assuming that I can solve for those properties that I'm after, starting from the QCD Lagrangian, which is obviously pretty hard, as we will talk about in a moment. Another thing to notice is that QCD would give this Lagrangian that I wrote down, in particular because of these gluonic interactions, it turned out, would give us a theory that is asymptotically free. By that, it means that the coupling constant of the theory, this alpha s, which is essentially g squared over 4 pi, has a scale dependence, an energy scale dependence that goes like 1 over 2 times a constant times logarithm of that scale over another energy scale called lambda QCD. This constant turned out to be actually positive for the number of quark flavors smaller equal to 16. Of course, we have 6 flavors in nature, and therefore this is a positive constant. What that means is that if we plot this alpha S as a function of Q, which is that energy scale, then what we see is that at low energies, this coupling constant could be pretty large, and at high enough energies, it would be something small, such that it would enable perturbative calculations in these ranges. As you can see, there are a bunch of data points that arise from various different processes and experiments that are being fit to the perturbative calculations to various orders using the QCD Lagrangian. And one of these data points is actually not perturbative. It is being performed using sort of lattice QCD. And it is lattice QCD that can actually push the determination of this alpha S to much lower energies, okay? But what is important to notice is that we will not be able to apply perturbative methods at ranges of energies that are essentially around 1 GeV or below. And this is where hadronic physics happens. So we really need non-perturbative tools to be able to describe the physics of hadrons and nucleons, which is really sitting in this region, okay? So then what can we do at these low energies? As I said, we can solve the theory non-perturbatively. This is why we're here. We're trying to learn in this course how to calculate non-perturbatively properties of hadrons and nucleons using the method of lattice gauge theories or lattice QCD, okay? Just as sort of a quick view of what lattice QCD is all about, it really starts from Lagrangian of QCD, right? All we have to do in this Lagrangian is to change the space-time integrals into sums, because now we're in a discretized finite lattice, right? So we're dealing with a finite dimensional system, and in the end of the day, we have to extrapolate to infinite volume, zero lattice spacing, and so on. But then the Lagrangian of lattice QCD is really based on the degrees of freedom of the theory themselves, the quarks and the gluons, some dimensionless quantity, which is related to the quark mass and lattice spacing, and again, some other dimensionless quantity, which is related to this alpha S, and again, the lattice spacing. So this is really the QCD theory in certain approximations that are systematically removable in the end of the day. And this is what we're learning in this course, and this is how we started to approach understanding how to discretize a continuum theory and be able to non-perturbatively approximate observables in this theory throughout this course. So I'm not going to talk too much about this front at the moment. And I want to talk about the other front, which is really effective field theories, okay? So here, we're not quite working with the QCD Lagrangian. It would have been nice if we could, but we are not doing that at low energies. However, what we're going to do is to realize that at low energies, the degrees of freedom are not these quarks and gluons of the QCD theory, but rather these hadronic objects like pions and nucleons and so on, right? So we're exchanging these fundamental level fields with hadronic fields, okay? At the same time, for input parameters of the standard model, the masses of the quarks, the coupling constant, now we're replacing those with the masses of these low energy hadrons, as well as a bunch of unknown constants. These are those coupling constants. We call them low energy constants, essentially because they're relevant only for low energy descriptions of this QCD Lagrangian, okay? So then I have this arrow here, and you may ask, what does it mean? Are we really starting from QCD to build this theory? Or are we just trying to build certain connections to the QCD theory? And other than that, it is rather an effective approach, and it's obviously the latter. But I'm gonna tell you how these connections are being made, okay? So this is going to be the topic of the rest of this lecture. All right. Importantly, as I will motivate us towards the end of this lecture, you will see that we actually need both lattice QCD and effective field theories to be able to really make progress in complicated problems in nuclear and hadronic physics. So we'll get there. But before that, let's really talk about effective field theories and how we can actually build them, make sense of them, apply them, and so on. Obviously, this is going to be a brief guide to this topic because it is very extensive and it requires many hours of discussions rather than just the next hour. Okay, so EFT procedure. So no matter what kind of effective field theory you're going to build out of a fundamental quantum field theory, there are usually a few steps or a few principles. When it comes to hadronic and nuclear effective field theories, these are the principles. We first start by inspecting the low energy spectrum of hadrons with regard to the symmetries of QCD and possible symmetry breakings. For each of these bullet points, I will give more explanations. Let me just mention them very quickly, and then we go through what these mean in a moment. The second bullet point says that we should write the most general interactions consistent with symmetries using only low energy degrees of freedom. Then we rank these interactions according to a momentum power counting. After that, we try to keep as many terms as we need for the precision goal of the calculation. Then we fix the coefficients of the low energy interactions that we kept in the previous step. And we do that by either fitting to experiment, or as we will see, to lattice QCD results. And then finally, we use the constrained effective field theory, at least to the order that we have kept, to be able to make predictions for all other observables. It turned out that this is pretty systematic, and there is a way to assign systematic uncertainties to our ignorance of essentially these higher order contributions to our effective field theory. Okay, so let's go through each of these bullet points one by one and understand what they mean. So as I said, we have to inspect the low energy spectrum of hadrons with regard to the symmetries and symmetry breakings of the QCD theory, okay? So what is this low energy spectrum? Here is a plot that shows you what various different hadrons, low energies are, and their corresponding mass, which is in this y-axis here. It's the mass in units of GeV, okay? So the lightest hadrons that we see out there are pions, obviously. And they're sitting at about 140 MeV. Then we have the kaons, we have the eta meson, and then eventually at about like 900 MeV, we have something like eta prime, this eta prime mesons. So this is interesting. You may ask, well, why do we have this sort of collection of 3 objects here? If you think about, like, zoom out, you have a collection of 8 hadrons here. And then this eta prime is kind of like isolated from this bunch. Why is that the case? On the baryon side, we see that we have the lightest baryons. These are objects that are made of primarily 3 quarks, although that's a more complicated picture. These are just the valence quarks, not a whole bunch of other things that happen inside neutrons and protons, obviously. But anyway, you get the point. These are objects with baryon number 1. And the lightest objects with baryon number 1 in QCD are about 940 MeV, neutrons and protons. There's a slight mass difference between the two, and this is because, again, there is a slight mass difference between the U and D quarks, and there's also electromagnetic interactions that affect protons and neutrons differently. They have different charges. In the same way with the pions and the kaons that are charged or uncharged, obviously. So we have these 2 guys, and then we have the lambda 0, sigma plus minus sigma 0, and then psi minus and 0. Okay, so there is 8 objects that are kind of sitting together as well. And now we're asking why such a pattern. Okay, we're gonna make sense of this based on the symmetries of the QCD theory. Okay, so let's go back to QCD Lagrangian and think about what kind of transformations we can perform, in this case on the quarks, such that the Lagrangian would remain invariant. It turned out that there are these transformations that we can imagine, okay? So there is the left-handed SU3 transformations, and I'll talk about these in a bit more detail. But what SU3 means in this picture is that consider just a theory of 3 quarks. Consider them to be massless. Obviously, they are not massless in QCD, but for all purposes, U and V quarks are pretty light and can be considered as massless. The strange quark, not quite. It's about 100 MeV in mass. But again, for the purpose of this discussion, let's imagine that these 3 quarks are massless. So by 3, then we mean the number of flavors of quarks that I'm going to keep. I'm going to forget about those heavier ones. They're not very relevant in low energy hadronic physics, right? So let's just consider 3 flavors. So SU3 means that I'm performing isovector rotations in the space of these 3 flavors of quarks. But whether the quark is left-handed or right-handed, I'm performing different types of rotations. Okay, so that's what it means by SU3 cross SU3 left cross SU3 right. Then there is the U1 vector and there is U1 axial. Okay, so U1 vector is really giving you the conservation of baryon number. And again, in a moment, I'll tell you exactly what these transformations look like. But this is just essentially changing the phase of each of these quarks flavors in the same way, in the same manner. Okay, so that gives you really essentially the conservation of baryon number. There is the U1 axial, and now this is again a phase, but it's kind of an axial phase. And this one is broken. It is broken by what is called a quantum anomaly. If you haven't seen that yet, that's fine. But eventually in your quantum field theory course, you will learn what a quantum anomaly means and what is a U1 axial, where you can find it in the standard model. Okay, and then let's come back to this SU3 left cross SU3 right. As I said, it is associated with the independent left and right rotations of these quarks, right? And then it turned out that it is broken down to SU3 vector. Why that's the case? Well, this is something that is called a spontaneous symmetry breaking. You probably have heard of this. This happens when your Lagrangian has the symmetry, but for some reason, the vacuum of the theory doesn't have it. It picks a particular vacuum, although it could have choices for picking something else that is associated with that symmetry. But once it picks a particular value associated with that vacuum, then it kind of breaks the symmetry. So the symmetry is broken at the level of the spectrum of the theory, but not at or the vacuum of the theory, but not at the level of the Lagrangian itself. So it's really a non-perturbative effect. You cannot see it by eye just by looking at the Lagrangian itself. You have to really perform non-perturbative computation to actually see that this is the case in QCD. So it turned out that there's a non-zero quark condensate in vacuum. Again, in a moment, I'll tell you exactly what this is. But what matters is that you started from SU3 left cross SU3 right. And now out of all the symmetry generators that you could have had, you're only left with the symmetry generators of SU3 vector, and in particular, SU3 axial is broken. And because there are 8 generators associated with SU3 axial, which are not there anymore, you're going to see 8 Goldstone bosons. Okay? Now, we have to remember that these quarks are not really massless. They have mass, but they're quite small compared to other scales in the QCD and in the hadronic spectrum. So because of that, we say that instead of 8 Goldstone bosons, we really have 8 pseudo-Goldstone bosons, meaning that their mass is not quite 0 as it should be for a pure Goldstone boson, but it's actually light compared to other hadrons in the theory. Okay? And another important consequence of this chiral symmetry breaking is the fact that it breaks parity, okay? And you can already see it from the level over here. Now we have only symmetry generators for SU3 vector, but we broke the SU3 axial, okay? So now there is an asymmetry of some sort between the parity partners in the hadronic spectrum. If you go and measure the masses of a parity doublet of a nucleon, for example, you see that it's quite different. It's about 1.5 GeV as opposed to 940 MeV, which is for the positive parity object. So this is interesting, and this is very consistent with the symmetry breaking pattern of the standard model. What are these 8 pseudo-Goldstone bosons? They're obviously those 8 objects, those mesons that we identified in the spectrum a moment ago, and we said they're bunched together and they're pretty light, okay? Let's look at that again. So these 8 mesons over here, they're really the pseudo-scalar mesons. These are the pseudo-Goldstone bosons associated with this spontaneous chiral symmetry breaking of QCD. And if I had only considered 2 flavors, that would be SU2 and left cross SU2 right, then we end up with 3 Goldstone bosons. It would have been more accurate because the U and D quark masses are pretty light. But because I considered also the strange quarks, now we're dealing with SU3, and therefore these are the 8 broken generators of the broken symmetry, and therefore these 8 Goldstone bosons. All right. What about this eta prime guy that is sitting up here? Well, it turned out that there is a connection between these guys and the fact that U1 axial symmetry is broken. If it would have not been broken, this guy would have actually bunched with these other guys. So that's amazing. We have been able to also associate another feature of the spectrum with a symmetry breaking pattern of QCD. Okay. So then what about the baryons? Well, as I said, we have an approximate SU3 flavor symmetry. And it turned out that a consequence of this is the fact that you can build essentially octets that transform under SU3 transformations like an octet objects. These are the 8 objects that you can imagine out of U, D, and S quarks that you can build. Okay. And there would be other multiplets that you can imagine that are higher energy in the spectrum. And that could enable really classifying hadrons in terms of their associated symmetries. And their symmetries, again, in the end of the day, are the symmetries of the QCD theory. So that's great. We have an understanding of low energy spectrum of QCD in terms of the symmetry and symmetry breaking patterns of QCD. Okay. So here's the exercise that will allow you to make sense of some of these symmetry transformations that I was referring to. And in particular, as you can see, we're going to start by identifying the SU3 symmetry by the symmetry associated with defining a triplet, and sort of SU3 triplet of U, D, and S. And therefore, we can then go ahead and define a bunch of different transformations on this triplet, Q. And these transformations are either of the form of U1 vector, which is going to give you a conserved current, and it would be easy to drive this conserved current and see that this is associated with conservation of baryon number in QCD. The associated axial U1, I haven't written down this in this exercise, but it would come essentially with a gamma 5 object in this notation, but let's not talk about that axial part because I don't want to get into the story of axial anomaly for the sake of this lecture. And then in part B, I'm introducing those SU2 left or SU3 left and SU3 right transformations, as I said, associated with the left and the right components of these objects, and obviously there is a typo here. QL means that this object times Q, and Q right means this object times Q. I'll fix this in the slides. But in any case, if we define these left and right components of these fermionic fields, then we can associate two different transformations, one with parameter alpha L and one with parameter alpha R. On these guys, you also notice the TA. This is what is called the generators of SU3. These are related to Gell-Mann matrices. And what these are, we are mixing the different components of this object, right? The U, D, and S quarks are being mixed under this transformation because this is an isovector transformation, in other words. But what is important about this is that we're transforming the left and right quarks differently. And what the goal of this exercise to actually show that in the limit of the mass of quarks being 0, this transformation does not change the kinetic part of your QCD Hamiltonian or Lagrangian. And in part C, we're going to bring the mass of the quark back. So we're going to have a mass term, and you're going to see that with the transformations that I've defined here, you are going to see a violation of the symmetry under these transformations. And that's why the mass breaks it. But if the mass is small, then it only breaks it by a little. So we can still have the symmetry and symmetry breaking considerations and proceed as I mentioned before. Okay, so with that notion, now that I understand the low energy degrees of freedom of QCD, which are these mesons and baryons, we would like to go ahead and write the most general form of interactions that would be consistent with the symmetries of the low energy theory. And remember, the symmetry is now the chiral symmetry. I've identified the pieces that would break the chiral symmetry, right, associated with this spontaneous chiral symmetry breaking. And we know that the Lagrangian of the theory itself is invariant under that chiral symmetry in the limit of course, massless quarks. So we should be able to accommodate that symmetry in the new Lagrangian that I'm going to write down, because I have identified the pieces that would be associated with the breaking of that symmetry. Everything else, that Lagrangian itself, should now be consistent with the chiral symmetry. Once we do that, we have to rank interactions according to a momentum power counting. What does that mean? It means that if we are at higher energies, we are going to have interactions that would scale with some powers of momentum. And if I'm interested in only low energy properties or processes, then those higher order momentum interactions are going to be less important, so I can ignore them. So we have to be able to organize interactions according to such a nice scheme. Eventually, we're going to keep as many terms as needed for the precision goal. Okay, so let's talk about this. So back to the question of chiral symmetry. As I said, we identified what it is that breaks the chiral symmetry of the QCD Lagrangian in the limit of massless quarks, right? So as I said, it is the vacuum of the theory. It turned out that if we look at the expectation value of this quark bilinear, this is a quark that is right-handed, or a Q bar that is right-handed with flavor J, okay, U, D, or S, times a Q that is left-handed with flavor I, and look at the expectation value of these objects in the interacting QCD vacuum. We're not going to see 0 in case where I is equal to J, meaning that if I'm looking at U bar U, D bar D, and S bar S, I'm going to see some non-zero value. It's written as minus some lambda cubed because this is setting the dimensionality, and lambda is just some mass scale that has to be measured, right? In fact, the value of this lambda is about 200 MeV or so, okay? So this object, if that exists, if we look at this expectation value, and we try to transform it with SU3 left or SU3 right transformations, because this is the right-handed and this is the left-handed, we're going to see a transformation that looks like LR dagger, okay? And therefore, we can imagine really two limits of this, right? So this expectation value does not go to itself unless L is equal to R, okay? And remember, these are unitary transformations. If L is really equal to R, then LR dagger is 1. And then this expectation value under this SU3 left, SU3 right is going to go to itself, which is good. And this is really the part that is unbroken. When L is equal to right, we're dealing really with a vector subspace or subgroup of SU3. And these are the ones that are unbroken, and associated with these 8 unbroken symmetry generators, there's this conserved isovector vector current, okay? Which is this object. Again, remember this TA is acting on the isospin components, the UDS components of these quarks, and gamma mu is associated with the Dirac structure of this object. So that's why I call this a vector isovector current, okay? Great. So what happens if L is not equal to right? If L is not equal to right, that would be essentially the axial subgroup of SU3. And if that's the case, we see that this expectation value does not go to itself. It violates the symmetry. And if that's actually non-zero, meaning that if lambda is really non-zero, which is the case in nature, then we're dealing with a situation where we have 8 generators of the axial vector currents. They're broken. So we're ending up with 8 Goldstone bosons. And what are those symmetry generators or currents that are broken? Those are going to be associated with the gamma mu gamma 5 or axial vector isovector current. So these guys are no longer conserved because of this property of the vacuum, but the vector ones are still conserved, okay? So that now puts in the context some of the things that I said qualitatively earlier, what exactly I meant. And this is what's happening to this symmetry of QCD once you have a non-zero vacuum expectation value for the chiral condensate. This is the name of this quantity. So then what do we do? Well, how if we define an object that essentially is related to this chiral condensate, right? And parameterize it with a bunch of fields. I'm gonna call them pi of x. And some other unknown coupling F, okay, or F sub pi, if you like. What is this pi object? Remember that we're dealing with generators of, so let's go back here. These Goldstone bosons are associated with the broken generators of the axial vector isovector currents. So I'm going to define this isovector matrix pi associated with those 8 Goldstone bosons. So in these parameterizations, I have objects that are called pi 0, pi plus, and pi minus, k plus and k minus, and k0 bar, and eta that are coming into this sort of 3x3 matrix, okay? And there's a bit more behind where these forms come from, but we don't have a lot of time to discuss that. So let's just take it that we can identify these low-energy degrees of freedom, put them into this sort of 3x3 matrix, and then ask ourselves, if these are our fields associated with these low-energy degrees of freedom, how can we write interactions or Lagrangians that then respect the chiral symmetry of the standard model? Remember, the standard model was supposed to be invariant on their SU3 left cross SU3 right. But the vacuum wasn't. This chiral condensate would break it. We take that chiral condensate, turn it into these pion fields. So now what is left is to just write Lagrangians that would then respect the rest of these chiral symmetry, right? So the way to do it is to take a trace, and trace is performed in this isospin space. And then I have things like kinetic operators, which is, these are bosons. So associated with these bosons, I would have the second derivative operator of sigma sigma dagger. There's also a mass term associated with these guys. And in order to find a mass term properly, we have to actually promote the mass matrix to a matrix of MU, MD, MS in the isospin space and define proper transformation properties in terms of SU3 left, SU3 right for this matrix. Put them together in such a way that once I perform those transformations under the trace, they will go to themselves. And therefore, I have my leading order chirally invariant Lagrangian for the pions or for the mesons, for these pseudo scalar mesons of the theory. Okay. So why do I say this is leading order? This is really kinetic operator plus the mass operator. There would be a bunch of interactions that would come out of expanding this object. Obviously, this has to be associated with sort of the SU3 unitary transformation. So that's why it has this form. So there would be a bunch of interactions that would come out of this. But using this sigma field, these are the leading interactions that I can write in order to get all the dimensionalities right and everything. There is this unknown coupling constant, F or F pi, that I have here. And once you actually fix it with an experimental measurement, in this case, turned out that it is related to the weak decay of the pion, is about 130 MeV, then you can make predictions at this order for a bunch of other properties. And I'll give you sort of an example in a moment. There is another coupling here, B, which turned out to be related to the chiral condensate. In particular, if you measure this chiral condensate using lattice QCD in this case, then you can have the value of this guy, and therefore the full Lagrangian here is really constrained. Assuming that we know the masses of the quarks, which is also the case. In fact, we can measure these guys using lattice QCD techniques as well. So really, we have a Lagrangian leading order, which is called the meson chiral perturbation theory Lagrangian, that would describe the interactions of pions, kaons, and the eta meson, which is great. Okay. So here is the exercise for you. We would like to try to expand the leading order chiral perturbation theory Lagrangian, this box in green. For these pseudo-scalar mesons, obtain the Lagrangian for the pion fields, right? So there are a bunch of other fields here. Just ignore those fields. Just focus on the terms that are proportional to the pion fields out of this expansion. Keep only terms up to 2 pions, no more. And then this should be enough to give you a relation between the mass of the pion and the mass of the UND quarks, as you will see once you do this expansion. Another thing to notice is that in the chiral limits means that when the masses of the quarks are 0, then pions and all pseudoscalar mesons should couple derivatively to R orders. This is a property of pseudoscalar as the Goldstone bosons, right? So that means that they do not really interact at 0 momentum. And this feature continues even when there is modal coupled to baryons and other fields in the effective field theory. And one question is, argue why this is the expected feature. It is related to the fact that these are Goldstone bosons, but you have to remind yourself of that argument as why Goldstone bosons only couple derivatively, and therefore they don't really interact at 0 momentum with other objects in the theory. All right, so now that we have this leading order effective field theory, how do we make predictions for observables, right? That's a big question. So we take that Lagrangian that I showed you over here. Now we expand it a bit farther. We keep more than just 2 pion fields in the expansion. Let's say that we keep 4 pion fields, which means that then I have interactions between 2 pions that can scatter off each other. That could be a term that is contained in this Lagrangian and would describe the scattering of 2 pions, okay? So then you do the expansion, you realize that at leading order, you only have a contact low energy constant, or LEC, and that's actually proportional to 1 over F pi squared. So once you fix the F pi, there is no unknown coefficient here to fix. Okay, so at leading order, it is actually the pion-pion scattering is fixed by pi and decay constant, which is great. And P is the momentum of the process coming out of those derivative couplings. What about next to leading order? When then you have to worry about these loop contributions. You can have two of these derivative couplings that would give you a factor of P to the 4 over F pi to the 4. But then you also have loops, and these loops turn out to be ultraviolet divergent. So they have some scale dependence once you regularize them. And then that's why they're proportional to logarithm of P squared over mu squared. Mu is some scale, right? Renormalization scale, which is not good. You don't want your observables to be dependent on some arbitrary scale. So then you realize that at the same order, there is another contact interaction with some unknown coefficient, okay? So the coefficient, although I write it as P4 to the F pi to the 4, there are 8 other low energy constants called Gasser and Lutwiller coefficients that arise because there are a bunch of different combinations of things that come out of that expansion at the next to leading order. So there are 8 types of them, and there are 8 low energy coefficients. And obviously there are these structures here that you have to account for and calculate exactly what the scale dependence of these loops are. Then from renormalized perturbation theory, you know how to deal with this situation, right? You know how to absorb the scale dependence of these guys into the scale dependence of these low energy constants that are in principle scale dependent at the same order. So once those scale dependencies are canceled out properly between these two types of contribution next to leading order, you will have a fully renormalized amplitude at this order, and you can make predictions with it. You can actually compare it with experiment because there's no scale dependence anymore, and it's a totally physical observable. So you're all set. So here is some results for doing that. So this is sort of the results of fitting these Gasser-Lutwiller coefficients to experiment using some phenomenological fits, and using the experimental data and some other analysis that would fit these LECs. And you see this point, which is this black point over here. There are also red points here. These are lattice QHD calculations of the pi-and-pi scattering that would enable you to actually fix those low energy constants and then make a prediction for the scattering length times the effective range of pi-and-pi scattering that are normalized by m pi squared. Okay, and you see that lattice QHD results that the physical values of the quark masses really agrees well with this other fixed to experimental data. We know that the chiral value, the value associated with a mass of pions being equal to 0, is set at this value 3. And we also have values for lattice QHD calculations at larger pion masses, because we can do that, right? And then you can actually perform a fit all the way through these 2 points to the physical point to the chiral point, and that would nicely agree with the leading order chiral perturbation theory. And that's remarkable that leading order chiral perturbation theory is already very good for pi-and-pi scattering. These not next to leading order corrections turn out to be not too large, okay? So this is how really this all works. If you want to make it even more precise, you keep going, you introduce more low energy constants, but then you have also more complicated interactions coming from the previous order coupling constants and the loop corrections and so on that you have to account for. But order by order, you make sure that you have a scale independent amplitudes, and then you try to refit all these LECs together to be able to then explain or experimental data or fit to the experimental data. Okay, what about baryons? So baryon chiral perturbation theory, again, is an extensive topic. I'm not gonna go through this either. I want to mention that if you recall, we had this bunch of 8 of these baryons that are sitting into a baryon octet. Again, we can organize them into a 3x3 matrix like so. Here is our proton, here is our neutron, but other objects sit at various different places. Now, this object should have particular transformation properties under these chiral transformations. And then we have a kinetic term for this object. And we have interaction terms for this object, the baryon objects, with the axial current, as well as the vector current, which is in this covariant derivative. So there are a bunch of things in this expression that might seem unfamiliar, and I haven't really explained exactly what these objects are. All you have to remember is that this is leading order baryon-Chiral division theory. There are these traces that would allow you to build chirally invariant objects out of these various fields. In particular, there are two unknown low energy constants of this order, the D coefficients and F coefficient, that turn out to be fixed by semi-leptonic weak decays of baryons. So once you actually fix them, you would be able to make predictions for other observables beyond the weak decays, like baryon scattering, for example, as we did with the mesons, right? Okay, so let's go back and form an effective field theory version of nuclear forces. Because remember, I started this course by telling you that phenomenologically, we built this nucleon potential, right? Can we actually make a potential out of these effective field theory interactions? And let us completely forget about these strange baryons, right? These hyperons. Let's just focus on protons and neutrons and try to build a proton-neutron type 2-nucleon potential using effective field theory approaches. And we were going to do that by what is called a Weinberg power counting. I tell you what that means. It was obviously first developed by Steven Weinberg in 1990s. And we'll see what the success of this program looks like. And we're going to see what the limitations of this program looks like for potentials, effective field theory potentials. But then after that, I'm going to tell you how to actually build these nucleon amplitudes as opposed to potentials using another power counting scheme, Kaplan, Savage, and Weiss. Okay, so that's the plan for the rest of this lecture. Okay, so potentials. As I said, I'm going to focus on Weinberg power counting. So I'm going to go order by order and tell you at each order in this perturbation theory or perturbative expansion, what are the important contributions that we have to keep. And I have 3 columns here. One is 2-nucleon force, 3-nucleon force, 4-nucleon force. I told you that 3 nucleon forces are important, even in building phenomenological potentials. So we have to be able to account for them in these effective field theory potentials, eventually 4 nucleon forces and so on. So let's just start from leading order. It turned out that in leading order, in this Weinberg power counting, there are only 2 types of interactions, either contact interactions between the nucleons, so these are those short distance contributions, or there are pion exchanges. So at this point, you may say, well, this exactly looks like how the phenomenological potentials build their potentials. Yes, up to this point, pretty much. But this is more systematic, and there is no, these are coming from those chirally invariant Lagrangians that we write down and expand order by order in some momentum Q over some breakdown scale of effective field theory, which we call the lambda chi Chiral division theory breakdown scale. Which is about, let's say, the mass of the row, which is like 700 MeV or so, okay? All right, so we have these 2 contributions, 2 types of contributions. Of course, there could be different low energy constants associated with different spin isospin structures here. And this form is pretty complicated. As I showed you before, it is the same here. You have to account for spin, isospin, and orbital angular momentum contributions in this form. Here is more details. So the leading order contact interactions or potential would look like a coefficient, a constant coefficient, C sub S, S for a scalar, and then C sub T for tensor. Your tensor part is proportional to sigma 1, sigma 2, where sigma 1 and 2 are acting on isospin space of these nucleons. Remember, this is kind of the notation. What about the 1 pion exchange potential, where it is proportional to both the sigmas and the taus operators that act on spin and isospin component. So sorry, for the notation, the sigma 1 and sigma 2 act on the spin space of the nucleons. Tau 1 and tau 2 act on isospin space of the nucleons. And again, you see the sigma 1 and sigma 2 that are dotted into the momentum transfer, or the momentum of the pion is exchanged between the nucleons. There is 1 over q squared plus m pi squared. This is associated with the propagator of a rather static pion. We're not interested in the non-static limit or dynamical limit of these pions for all purposes. This potential with the static pions describes nuclear physics pretty well. And you see a coupling constant here, which is called GA. I'll come back to where this comes from, but you also see this familiar pion decay constant that are sitting behind us, right? So you see the pion physics, you see the nucleon pion physics out of these couplings, and you see this spin isospin components. The ones who Fourier transform and go to the positional space, you're going to see the familiar objects that I showed you before for this part. So here's the exercise that would allow you to see that. So exercise number 5 is asking about the fact that in principle, there are 2 other spin isospin structures for the 2 nucleon contact potential at the leading order, right? So look at this. I have only 2 terms, but in principle, you can think about 2 other terms. The question is, what are they? And then you should argue why only 2 terms are written in the potential that I showed before, and I kind of forgot or ignored the other 2 terms. And you should be able to answer this based on those symmetric considerations that we had before. And again, we can discuss this more in the class. So that's why there are only 2 coefficients that here and not more complicated structures beyond these 2 at this order. Exercise number 6 would tell you where that pion exchange potential actually comes from, starting from chiral Lagrangian. What I didn't show you before is an expanded part of the chiral Lagrangian for the baryons. Remember, I told you I'm not going to tell you anything about this form. We're not going to expand it or anything. The only piece that we need out of that expansion is really this pion nucleon interaction, which is proportional to what is called an axial charge of the nucleon, and has the following form. There are your nucleon fields, but there is also the pion field. There's a derivative that is acting on the pion field, because pions only couple derivatively to the other objects in the theory, just as before. And then there are these tau and sigma matrices that are in this form. Okay, so this is the form of the Lagrangian. And now we consider Feynman diagram for the exchange of a pion between 2 nucleons. So essentially the diagram that I showed over here, this guy, okay? Each of these dots is going to be described by this Lagrangian because it describes the interaction of a pion and 2 nucleons, right? It also depends on the propagator of the pion, the guy that is sitting in exchange between. There's a propagator associated with this. And you can take this propagator to be this static or instantaneous potential or propagator for the pion, which has the following form, okay? So now if you use your QFD knowledge, write down the Feynman rules associated with the interactions of the pions and nucleons from this, and then read off your Feynman diagram, you should be able to actually drive this form, this pion potential in momentum space, just by simply reading off what is associated, the Feynman rule associated with the pion-nucleon interactions, and then multiplying them out by this pion potential. That should be easy, okay? Then you can actually Fourier transform to position space. Okay, so you have the Q, but there is an associated R, Fourier conjugate to the Q, which is R, which would be associated with the relative distance of these nucleons. So if you do that Fourier transform, you should be able to see, for example, that central and tensor components of the one pion exchange that I talked about before. And then part C is asking how does the strength of the two pion potential compares between iso singlet, the total isospin equal to 0, and iso triplet, total isospin equal to 1, two nucleon channels. So again, remember that this potential has very interesting dependencies on both spin and isospin objects here. And therefore, once it acts on a channel with total isospin 0 or 1, which means that total spin 1 or 0 respectively, is going to give you different coefficients that come out of that potential. So you should be able to actually compare the strength of this potential between the two primary channels that we're interested, iso singlet and iso triplet, two nucleon channels. Okay. So again, a slightly non-trivial exercise, but pretty straightforward if you have seen QFE perturbation theory before to be able to manage this exercise. Again, we can go through this during the class. Okay, so that was just for leading order potential. What about higher order potential? It turned out that next to leading order is not actually Q over lambda for various reasons. It's actually Q over lambda squared in Weimeric power counting. How does it look? Well, there are contact interactions. These are going to be derivatively coupled and so on. So there are more types of these contact interactions that you can come up with different spin isospin operator structure. But then importantly, you also have these two pion exchange potentials of various forms that you have to account for. And sounds complicated, but people have successfully dealt with these objects. Not only that, they have also successfully dealt with next to next leading order as well as higher order potentials. Okay, so at next to next leading order, we're going to have more pion potentials, but with new couplings that we have to identify in the theory, in the Lagrangian again. And then importantly, at this order, we are going to see for the first time, it turned out the three nucleon forces. They could either be the result of the exchange of two pions between three nucleons, or the results of these new contact couplings between three nucleons themselves, or between two nucleons and the pions. And this is again the first order that we're going to see this three neutron force, the three nucleon forces in this Weinberg power counting. What about higher orders? Well, impressive calculations by various groups have allowed us to go even to an N3LO. And that means that this is the order that you're going to see 4 nucleon forces. So this is one example. This is not the only example. There are going to be contact 4 nucleon forces and much more. But I have just shown you a couple of examples that are shown in this review article that you can check out. Okay, so this is how it works. You really start from your Lagrangian, and then order by order in some power counting, number of derivatives, and so on, and you will be able to identify the contributions to your potential at each of those orders. Okay, so then what is the usefulness of all of this? Well, there's a bunch of impressive results out of this program. So at lowest order, there are only 2 partial waves, right? There is 1s0 and 3s1. These are those isospin 0 and isospin 1. So this is isospin 1 and isospin 0 channels, which are called 1s0 and 3s1. And then there are experimental data. So you can go ahead and really fit to these experimental data order by order, and be able to then reproduce what's known by which is this like Nijmegen experimental data. Okay, for example, there are also D waves and SD mixing parameter in the iso singlet channel. So in principle, you can also look at the experimental data and then try to fit those parameters as well. Okay, but once you do that, in principle, you should be able to then make predictions not only for higher energies or higher momenta, but also for a bunch of other channels that might actually share the same low energy constants with the channels that you've already fit to experiment. So at that point, you start to make predictions. And these are various different partial waves, and the bands are associated with fitting from leading order to next to leading order to the higher orders, and identifying how much of systematic uncertainty you're making out of this systematic expansion. So as you can see, despite the phenomenological potentials, here now there is a power counting scheme that would allow you to count the importance of these operators given the energy scale that you're dealing with, and associate quantifiable error bars to these predictions. Okay, what else can you do with these EFT potentials? Well, you can even go ahead and predict or post-dict the spectrum and charge radius of a bunch of light to medium mass nuclei. And this is, again, a result I got from this preprint over here. Experiments are these stars that are in green, the leading order, next to leading order, and next to next leading order predictions of this theory. As you can see, leading order predictions are away and they have large error bars. But as you get closer to higher order predictions, they pretty much converge to what the experimental values are for most of these observables, which is remarkable because we're talking about fitting only 2 nucleon and 3 nucleon observables to get these low energy constants, and eventually being able to predict something like the spectrum of oxygen 16, right? So this is really shows you the predictive power of these effective field theories. In principle, of course, they are going to fail at some point, but this for certain low energy, low density observables, they seem to be doing pretty well. Okay, so now that we saw these success stories, we have to ask ourselves, what is the limit? What are the roadblocks? Okay, well, the first thing is that the potential in Weinberg power counting is systematically counted. In other words, we go from leading order to next to leading order and so on, and associate a power counting to this potential, right? But on the other hand, the amplitude is not. Why do I mean by that? What do I mean by that? Well, the amplitude is essentially not only the potential, right? But once you solve the Schrodinger equation for these many body problems or few body problems, what you're actually doing is to iterate the potential to all orders, right? This is what you do, for example, in Lippmann-Schrödinger equation. You give me the potential, I solve the Schrodinger equation. Although I started from, for example, leading order potential, now I have 2 leading order potentials that are connected with a loop and so on. So the potential is at a given order, but once you solve for the amplitude for the observable, then you really mix up everything, all that power counting that you built into the potential. And that could be problematic. And in fact, it shows up on a scale dependence of your amplitude. If you had done this systematically at the level of amplitude, order by order in perturbation theory, you're not going to see that scale dependence of that order. But once you do this and you look at your amplitude, you're going to see that it's not actually a scale independent. So you have to change the cutoff in various ways to then make sure that your observables are converged, okay? So in these calculations, they need to deal with the residual cutoff or scale dependence at any order in the EFT, which could be problematic, but you have to be very careful as you do that, okay? So now you may ask, why did we decide to count the potential as opposed to the amplitude, okay? And I'm gonna introduce another scheme that actually counts the amplitude directly, okay? So we're gonna look at how to organize interactions according to their importance. As I said, in Weinberg power counting, pion exchange as well as contact interactions were at leading order, the 0th order. However, we can change this sort of naive dimensional analysis picture and try to do better, as I'll explain what I mean in a moment, okay? So consider the simplified form of contact Lagrangian and leading order. and at next to leading order. And I'm ignoring all spin, isospin structures, okay? So at leading order, a contact interaction is going to be N and dagger and dagger. So these are those 4 nucleonic fields. It's going to be proportional to some sort of low energy constant, okay? And whether it's Weinberg power counting or Kaplan-Savage-Wise or KSW power counting that I haven't introduced yet, doesn't matter. It's going to be some coefficient multiplying this operator. And then at leading, next to leading order, you're going to have derivative operators. You cannot have just one of them because you break Galilean invariance in this case. But then you have 2 of these operators, and then it's going to be therefore proportional to another coupling called, say, C2, okay? And I call it C2 because it's proportional to a term with 2 derivatives as opposed to 0, okay? So this is a very simplified picture of these contact interactions of leading order next to leading order. Let's ask ourselves what the mass dimensionality of these low energy constants are. It's easy to verify that the mass dimensionality for C0 is mass to the -2, and for C2 is mass to the -4, okay? And these are a few hints as how you can come up with this. You just count the mass dimensionality of your Lagrangian, your nucleon field, and your derivative field. And what you're going to see is that the C0 and C2 have the following mass dimension. Okay? So that's trivial stuff. Now, let's ask ourselves that if I have 2 nucleons, I'm going to look at their scattering amplitude. How can I parameterize that scattering amplitude at low energy? Well, this is just non-relativistic nucleons scattering. You have seen in quantum mechanics course how to describe low energy scattering of 2 particles in terms of a scattering phase shift, delta, right? And it's going to have the following form. It's 4 pi over the mass of those objects that are scattering, in this case, the nucleons, times 1 over p cotangent delta minus I times p, where p is the relative momentum between these scattered nucleons, okay? You have also seen, hopefully in your quantum mechanics course, that low energies, the p cotangent delta, so this is like a generic form, right? But we can now go ahead and take p cotangent delta and expand it in some powers of momentum. In particular, at low energies, we're going to have a constant term, I'm going to call -1 over a, where a is the scattering length, and then a term that is proportional to p squared, and the proportionality constant is r over 2, where r is called an effective range. There are higher order terms here that I'm not going to write down, all right? So again, the 2 nucleon scattering amplitude can be parameterized by a scattering phase shift. If I just have 1 single channel, can be parameterized by a scattering phase shift in that channel. But then at low energies, I can take the p cotangent delta and momentum or Taylor expanded in p squared. Now, there are 2 choices that you can imagine here in terms of taking this object as a whole and expanding it. There are 2 options. If A, this scattering length is small, in other words, it's proportional to 1 over lambda, where lambda is a breakdown the scale of the EFD, and it could be pretty large, then we look at this expression and we say, all right, 1 over A is a small, right? So then I can imagine an expansion that looks like the following: 4 pi A over mn, and then I have the first term, which is a constant, the second term, which is proportional to A times P, and then the next terms are proportional to A times P squared and AR P squared and so on, right? So if A and the R and everything else is small, then I can have an expansion that looks like this, okay? But how if we are in a regime or in a theory where the scattering length is actually large? And I would call that an unnatural scenario as opposed to a more natural scenario. And by large, we mean that if we are at low energies, we can approximate A with 1 over P. Remember, P is small. At low energies, this is a small number. So if A is of the order of 1 over P, I'm not allowed to do an expansion that I did over here. I rather pull out 1 over A plus IP out of this expansion. and then have terms that would go like 1 over a plus ip times p squared and so on. Because remember, these two guys are of the same order, so they have to be kept together, okay, according to this. So I really have two different momentum expansion. One I would call natural and one that is called unnatural. So then the question is, what is nuclear physics? What do we have in nature? If I look at nuclear-nuclear interactions in nature, are we actually in scenario 1 or scenario 2? Are these interactions natural or unnatural? Well, experimentally, what we have observed is that the scattering length for one S0 channel in two nucleon force channels is minus 23 Fermis. You have to compare this really with essentially 1 over m pi. So we're talking about something of the order of 1 Fermi, which is really sets the range of interactions and or this effective range over here. And that's pretty large in terms of the magnitude, right? For 3s1, we have 5 Fermis, which is still pretty large compared to 1 or 2 Fermis that we expect to be the range of interaction, in particular, what we get for the effective range, which really sets the range of the interaction, in other words. So we really are dealing with scenario number 2 in nuclear physics, and this is the expansion that we have to think about. So what does this mean for the low energy constants that I mentioned before? Well, if this is the amplitude, and I try to write this amplitude in terms of low energy constant, then at leading order, I just have one of these C0 coefficients, right? So now I have to compare this C0 coefficient with the leading order term that comes out of this, which is really this guy in scenario number 1, and is this guy in scenario number 2. So in scenario number 1, C0 is really proportional to 1 over lambda mn. Why? Because it's proportional to 4 pi a over mn. A is like 1 over lambda, so C is 1 over lambda times mn. Scenario number 2, C0 goes like 1 over p times mn. Why? Because it goes like 4 pi over mn times 1 over a, which is of the order of p, and ip. So it's really proportional to 1 over p mn. Remember, lambda is large. It's the breakdown scale of the theory. P is pretty small. So we're talking about a few MeVs as opposed to hundreds of MeVs over here. And that's interesting because what that means is that if we are in the natural case, the leading order LHC has its naive dimensional scaling. It goes like 1 over mn, and what is left to really compensate for the next mass scale is really this breakdown scale, which is lambda. But if you're in the unnatural case, you're not really compensating for the scale of this operator by lambda, but rather by the momentum of the process, okay? So in this sense, we say that these leading contact LECs are promoted to essentially lower order than they appear. Okay, they are large and their contribution should be included to all orders. If C0 would have been small, I would just stop at this order and don't worry about the rest. That would be my leading order. But how if C0 is large and I have to account for it to all orders? This is what happens actually in nuclear physics, okay? So we have to be careful. This is what the essence of the KSW power counting is. The fact that leading contact interactions are summed to all orders, and pi connections actually comes at next to leading order. So that's the difference between Weinberg power counting. All right, so here is a look at how things go. At leading order, turned out that everything goes like 1 over p. So this is unlike the power counting in Weinberg. The leading order amplitude is actually not q to the 0, it's actually q to the -1. Okay, because of this argument. That means that if I expand this to all order, the first one goes like 1 over p. The next one is going to be a loop contribution like this with 2 of these C0 couplings. Each of those C0s would go like 1 over p. It turned out that this loop would go like p. And in fact, we want it to go like p such that we can reproduce this expansion that we have over here. Okay, but sort of this is our inspiration for thinking that this loop should really go like P, so that this term would also be 1 over P. This term, which is the second two loop contributions to the amplitude, that would also eventually go like 1 over P because of this. So we have now an expansion of the leading order amplitude where each term is P to the minus 1. It has to be summed up to all orders. It turned out that for this amplitude, we can actually sum it up to all orders. Let me show the results. If we do that, we have essentially this. You see the scale dependence here. Shouldn't be surprised. We are dealing with the loop contribution. And this loop contribution is actually finite in 3 plus 1 dimension, but it is not in 2 plus 1 dimension. And there is a power counting scheme that KSW introduced that would allow you to subtract the pole in lower dimension, such that with that scheme, you're going to get a loop contribution that is proportional to P, which is what we want. So if you then sum this geometric sum, assuming that power counting scheme to evaluate this loop contribution, what you see is that it's minus C0 over 1 plus C0m or m sub n over 4 pi, the scale plus IP. Okay, so that's the leading order amplitude. And it's, again, goes like 1 over P. What about next to leading amplitude? There are a bunch of things, okay? And let's just focus on the first term in particular, because the rest of the terms are important if I have pions explicitly in my model. If I can ignore those pions, I can actually absorb everything in this sort of term. And this m pi squared term, which turned out to be important. But in any case, let's just look at this first term. There is the C2 coupling, and it's proportional to those two derivatives, so that comes with P squared. But then these legs should be dressed to all orders with these C0 interactions, because these C0 interactions are important. They're leading order. They go like 1 over P. I can't ignore them. So not only we have to account for this, but rather we have to account for, let me see, I should have, okay, this picture over here, where this dressing means that I either have no interactions or I have these interactions that are coming out of this leading order contribution, okay? So that means that all amplitudes, not only this leading order amplitude, but rather all other amplitudes would have some notion or dependence on the C0 coupling, because they're dressed on either end or in between, depending on the diagram, with these contributions from leading order. And they are then proportional to the C2P2, okay? So this is how power counting in KSW works. You have P to the minus 1 at leading order. It has to address all the diagrams. And then at next to leading order, you have P to the 0, and you have also these pion exchange diagrams, rest pion exchange diagrams, and so on and so forth, okay? So again, there is an exercise here that would allow you to actually drive both the leading order and next to leading order amplitude proportional to C0 and C2. Here is an explanation of how that can work. Again, I talked about this power divergence scheme. There's some more explanation here. And this is the non-relativistic nucleon propagator that you have to take. And then once you do that, you should be able to then drive these leading and next to leading order amplitude that I showed in the previous slide. Okay, so that's another interesting exercise or calculation that would allow you to understand where some of these results come from. And if you need help, just let me know. Hopefully we get to go through some of these in the class, but probably not all of them. So we will see. Okay. All right, so where are we going with this? So in the case W power counting, therefore, there is no cutoff or renormalization dependence that remains at any order in the expansion. Why is that? Because I'm just expanding the amplitude. And I'm making sure that at each order in the amplitude, I have a scale independent quantities, meaning that the C0 dependence on the scale is going to cancel out the dependence of in such a way that the amplitude itself is a scale independent, in the same way with the C2 at next to leading order and so on. So there is no notion of potential, rather the notion of amplitude, which is physical and is scale independent by construction, order by order in perturbation theory. Okay, so how does it look like? So one S0 channel, let's go back to an NN scattering phase shift, delta as a function of momentum. At leading order, it doesn't quite work well compared to experiments. If you do next to leading order, you get closer. If you do NNLO, you get even more closer, okay? So it turned out that this scheme works really nicely for the 1S0 NN channel. This is the channel that Weinberg power counting doesn't quite get, okay? It doesn't quite sort of converge in terms of a perturbative expansion in the 1S0, although it does very well in 3S1. On the other hand, KSW turned out to not work well in 3S1 channel. There are some convergence issues. Turned out that in 3S1 channel, the pion exchange potential is more important. So it's not a good idea to actually keep it in next to leading order. In Weinberg, we keep it in leading order, and we iterate it to all order, essentially, in solving for observables. So there are some interesting situations. There's an interesting situation here. We have introduced two power countings. They have convergence issues depending on what nucleon channels we're dealing with. It turned out that these are not the only power counting that exist. They actually initiated a bunch of other studies on power countings with better convergence in both channels, but those are more involved. And in fact, this is still an open question. We don't have the best power counting for all scenarios, for all energies, densities. And whether these power countings are applicable to heavier nuclei is not yet established carefully. We need to be very careful in arguing how predictive these effective field theories are as we move towards larger systems and more involved predictions. But what is important here in this program is that we still need experiment or lattice QCD to constrain the EFD coefficients. In particular, if we want more precision, we go to higher order. In higher orders, there are more and more low energy constants that we have to fit. And at some point, experimental results might be limited. And there may be situations that there's absolutely no experimental results. For example, 3 and 4 neutron forces. There is no experiment that would allow you to collide neutrons at low energies, just very hard, just because of the Pauli exclusion principle. But we know that these forces are important in dense neutron environments, in the interior of neutron stars, for example, or in these neutron-rich isotopes. So how do we actually constrain those forces? Well, that's where we have to solve QCD to be able to provide the data that is required to constrain the coefficients of these forces, whether in your Weinberg power counting or KSW or some other power counting. We really need these data points to be able to pinpoint what the LECs are and then make predictions for larger systems. Hyperon nucleon and hyperon forces. Remember, we just talked about nucleons in the later part of this talk, but we started by talking about lambda baryons and sigma baryons. These could be very important in the interior of neutron stars. It would be important to know how they interact with nucleons, with themselves, such that we can make reliable predictions for equation of a state of these dense environments. Matrix elements of various currents. Remember, we talked about things like weak interactions and neutrinoless double beta decay and so on. And we said that some of these experiments, we don't have data, right? For neutrinoless double beta decay, for example, we don't really have the data. We want to make theoretical predictions for what the matrix elements associated with those processes are. So then in the end, our hope is that lattice QCD would be able to constrain the low energy coefficients of the corresponding effective field theories for those processes. And this is a very active program and it's still ongoing. And we're trying to really sort of push the limits to be able to provide input or QCD input for processes that we don't have access to experimentally, but are very important in addressing the questions that I said in the beginning of the talk. Okay, so then as it is about this, all about this course, given all these limitations, why not calculating everything with lattice QCD? Of course, we come back to this question later. We are trying to learn how to actually establish that throughout this entire traineeship course. But I think this should give you already the motivation for why we care about calculating certain observables in hadronic and nuclear physics using lattice QCD, because not only they can directly tell us something about those hadrons and nucleons, they can also be the input to these effective field theories, such that we can use these effective field theories and make predictions for larger systems and denser systems that are not really accessible to QCD or lattice QCD methods at that time. All right, thank you very much, and I hope you enjoyed this course.